All right, good morning. So what we're going to be talking about today is Chapter 35, Refraction. And so I'll give you a minute if you can open up your text to page 679. And this is our next chapter in the text. So we're going to talk about a concept called refraction. The textbook talks about refraction in terms of light. When we get to the chapter on sound, refraction is not discussed, even though sound does experience refraction as well. So that's why we're only going to spend a couple of days here on refraction. But it's an important concept that you need to be familiar with. And we'll also, this week, we'll do a lab on refraction, so you can actually experience it and do some calculations related to refraction. So on page 679, at the top of the page, you have this figure 35.1, which is really just a very general graphic which shows what's happening with refraction. So we have an incoming light ray that exists in medium 1. In the textbook, they're suggesting that medium is air. It could be anything. In this case, we'll say it's air. And then the light ray strikes a second medium, which is also transparent. And then, as the light ray enters this second medium, it changes direction. And so you have an angle of incidence, and this is the theta with the subscript r is not angle of reflection, now it's angle of refraction. And the light ray changes direction, and then when the light ray then exits the other side of medium 2, it changes direction again. And I don't know how clearly I've drawn it, but this is a reversible process. So the light ray exiting medium 2 and going back into medium 1 resumes its original path. It's offset some, but it's a parallel path. Okay, so then we can say that speed of light is a constant in a given medium. Remember, we back in an earlier chapter, we said speed of light is frequency times wavelength, where the speed of light is a constant. However, that is only true in a given medium. So as long as this light ray kept traveling in air, the speed would not change. However, once this light ray enters this second medium of a different density, then the speed changes. So we could say that if the medium changes, then the speed and direction also change. And we'll talk a little bit in one of the later sections, in a few pages, we'll talk about what the mechanism is that suggests why that happens. There's another graphic which just illustrates the what you might see in refraction, and this is something that you may have all seen at some point or recognized that there was something unusual going on. So let's look at that graphic 35.2 at near the bottom of page 679. So this is a situation where some kind of object is underwater, and you're an observer outside the water, and what you see in terms of the underwater object is not actually where the underwater object is, because as the light rays reflecting off the object exit the water into the air, the direction changes. So you get fooled into thinking the object is somewhere that it really isn't. And you may have noticed that, like if you dangle your feet off the edge of a pool or somebody's underwater, that their location is a little bit offset. So we can actually, I don't know how well you're going to be able to see this on the camera. So I have a little similar kind of demonstration here. I don't know if you can see that. So here's a beaker of water, and there's an object in the water. Let's pull it a little closer here. An object in the water, and there's this brass rod. So you can see some of the brass rod is out of the water in the air, and some of it's in the water. So you can see that this actually is one solid rod, and it's straight. But we're getting a little distortion there below the water line because the light rays are changing direction. Okay. All right, so now we're going to move on to the next section on index of refraction. So now we're at the bottom of page 679. There's the first section, 35.1, is called Index of Refraction. So the purpose of the index of refraction is to compare the speed of light in different materials to the speed of light in a vacuum. Now we know from a previous chapter that the speed of light is 3 times 10 to the 8th meters per second. And that's in a vacuum. But we also use that value for speed of light in air as well. Air does not significantly slow down the speed of light compared to a vacuum. So this index of refraction is, and we're going to use the letter N for index of refraction, lowercase n. And it's the ratio of the speed of light in a vacuum to the speed of light in a given material, whether it be water or glass or whatever kind of other transparent materials we're dealing with. So here's the equation. Once again, one of these simple three-term equations. Index of refraction is C over V, where N is the index of refraction, C is the speed of light in a vacuum, that's our value of 3 times 10 to the 8th meters per second, and then V would be, the velocity would be the speed of light in some given medium. The table, the book gives you a table on page 680 of the index of refraction for a variety of materials. So if you could take a look at that, table 35.1 in the middle of the page, page 680. Now you'll notice that index of refraction is one of those terms we deal with which does not have any units, because you're dividing a speed by a speed and all the units cancel out. So n is just a number which will tell you how much is the speed of light being slowed down in a given material. So in this table you see a variety of transparent materials, transparent meaning that light will travel through. And some are solids and some are liquids. You'll see diamond has the highest index of refraction, so light would go slow, would travel slower through diamond than any other material. And so you almost could say that the more dense a material, the slower the light will travel through it. So let's exercise this equation looking at example 35.1 on page 680. Okay, in this example, you're asked to find the velocity of yellow light in diamond. Now, why do they say yellow light? Well, you remember back in chapter 33, we did look at the visible light spectrum, and you have all different colors of light, and every different color has a different wavelength, and so they're just specifying for you yellow light, but we're just going to use 3 times 10 to the 8th meters per second for C. So we're trying to find the velocity of light in diamond. So we're going to use this equation. Index of refraction is equal to C over V. We're solving for V, so you have to manipulate the equation. So using algebra, it manipulates into this form. And so now you just plug in what you know, 3 times 10 to the 8th meters per second. Now for diamond, the index of refraction is known, so you just go look it up in the table. Table 35.1 tells you diamond has an index of refraction of 2.42. Then you just get your calculator out, and that ends up being 1.24 times 10 to the 8th meters per second. So almost 2.5 times slower than the speed of light in air. So that is a significant slowing. Still moving along pretty fast though. All right, so now let's go on to practice that a little bit. Let's go to the end of the chapter and do an end of chapter problem. So this is problem 35.1. And that's back on page 693. All right, so take a few minutes and work that problem. You're asked to determine for some unknown transparent medium, what's the index of refraction using the given information. So go ahead and take a few minutes to work on that one. Okay, so problem 35.1, you're asked to calculate an index of refraction. We don't know what type of material this medium is. However, we are told the speed of light in that medium. And that is and you'll notice, as we discussed earlier, that all the units cancel out, so you're left with a unitless number, and you end up with 1.88. And again, the text is just continuing its routine of rounding everything to 3 significant figures. All right, and let's go ahead and do one more. Problem 35.3. It's a four-part problem. However, let's just do the first part. You're asked to calculate the speed of light in 4 different mediums. And let's just do the first one. 35.3 is asking you for the speed of light in crown glass, and you can look up the index of refraction in the table earlier in the chapter. So we'll just do the first part. We'll call it Part A. And you're asked to calculate the speed of light in that medium. Now, you're going to get a little bit different answer than what's in the text. I think on that particular one, I think they just made a little error and may have used the wrong value for index of refraction for crown glass. But let's go with what's in the table in the book, and your answer will just be slightly different. So take a few minutes to do that. Okay, so to calculate speed of light in crown glass, you'll need to look up the index of refraction, and from the table earlier in the chapter it ends up being 1.52. We'll use our same equation, but we're solving for speed of light. And if you work that in your calculator, you should get 1.97 times 10 to the 8th meters per second. And the answer in the book is given as 2. I think that was just an error. There was no intention for them to round it from 1.97 to 2. So hopefully this is what you came up with. All right, so now what we're going to do is let's now move on to the next section, which is the laws of refraction, starting at the bottom of page 680. Section 35.2, laws of refraction. So this is just a duplicate of this figure 35.3 at the top of page 681. We looked at this earlier. So what we're suggesting here is we have a light ray going through medium 1, striking a transparent medium 2, and then passing through the medium 2. And these angles are measured, as we did in an earlier chapter, with respect to a normal line, which is perpendicular to the surface of the medium. So we have an angle of incidence and an angle of refraction. And we, just like we did with plane mirrors, we are going to say that the incident ray and the refracted ray and normal line all lie in the same plane. So we're just talking about a two-dimensional situation here. Makes it simpler to talk about it and to solve problems related to it. Another one of the laws is that the path of the refracted ray is reversible. So what does that mean for us? So this is the left side sketch at the top of page 681. So we have an incident ray coming through medium 1, refracting through medium 2. Now let's say we have the opposite situation. Let's say actually the light ray is originating from medium 2, so it's going in that direction, and then it leaves medium 2 into medium 1 and refracts and heads in that direction. In other words, the path is going to be the same. Let's go back to the original setup here. Let's say that the light ray is originating in medium 1 and refracting through medium 2. So what we can also say as a law is that a light ray entering a more dense medium turns towards the normal line. So what would be an example of this? So let's say, for instance, let's say medium 1 is air, and let's say medium 2 is water. Water is more dense than air. Water is a liquid, air is a gas. So that's exactly what you're seeing here. Once the light ray leaves medium 1 and refracts through medium 2, it changes direction by turning towards, it turns towards the normal line. So that's the direction change. And then we can also say the reverse of this. The reverse is, let's say that the light ray, again, let's say it originated from the water and then exited into air. So you can, the opposite of this is true. A light ray entering a less dense medium turns away from the normal line, which is what you're seeing here. And that's what was happening when when I showed you the beaker of water with the brass rod sitting in it. That the light rays leaving the beaker of water out into the air where you could see them were actually being refracted away from the normal line. So you thought that the object was actually down in here rather than down in here. So a light ray entering a less dense medium turns away from the normal line. So then the question is, why does this happen? So there's a really good analogy shown for you in the text. If you can look in the middle of page 681. What's an analogy that might help explain this situation? So in this case, what we're illustrating here on the right-hand side of that figure is, let's say you have, and you've all kind of, you may have experienced this, hopefully in a safe way. You know, if you're driving down a rural road, which has kind of like a gravel shoulder off the side of the road, and let's say you're driving down this road and you wander a little bit, and your car, your passenger side tire, front tire, actually drifts off the road a little bit and kind of digs into that gravel shoulder, then what's going to happen to the car? So what's going to happen is you have your left wheel still on the smooth pavement, your right wheel is now on the gravel, so the right wheel is going to start slowing down. And if you have your right wheel slowing down and your left wheel still going on the pavement, the car is going to tend to turn. And you may have experienced that a little bit. The car will tend to pull to the left because of that situation. So in trying to use that analogy with light, then here's what is being suggested. In this case, remember we said that light sometimes acts like particles or photons, and sometimes light acts like a wave. Well, if you use the wave behavior here, you can try to explain this. So let's say instead of like a particle, let's say this light is like a wave. So you'll see that once this wave strikes this medium 2, you get part of the wave in entering medium 2, and another part of the wave hasn't really got there yet. So this part of the wave starts slowing down. This part of the wave is still moving along at the same speed. So the whole wave tends then to turn. And then once the wave enters the medium, then it just goes in a straight line. And then you get the same thing happening at the other end. So that is one way to explain what's happening. All right, the next thing we're going to talk about is a law called Snell's Law. Snell's Law is discussed on page 682. So let's get set up for that. Now we're at the top of page 682. This whole page is really being used to develop something called Snell's Law. It's a derivation, so I'm not going to quiz you on this. You should be able to use the equation, but this whole page is just showing you where it came from and what's going on. So I've just recreated the sketch at the top, figure 35.5, and I just want to discuss it for a minute so you can just kind of know where it came from. If we had an hour in class and that's all we had to do, we could easily work through it and you'd be able to handle it fine. So what is Snell's Law? So it's used to predict the angle of refraction if you know the two mediums that are in play. The other thing it can be used for is to identify an unknown medium if you're able to measure the angle of incidence and the angle of refraction. In fact, that is what we're going to be doing in our refraction lab, is you're going to have a couple of unknown mediums and you're going to measure angle of incidence, angle of refraction, and then use Snell's Law to see if you can figure out what the actual medium it is involved. So again, you're not responsible for this derivation, but now one of the things involved here is trigonometry, the sine function in trigonometry. So let's see a show of hands. How many people here in class have had trigonometry in previous schools before South Hills? Oh, it looks like everybody raised their hand. So you're all familiar with trigonometry. That's great. I'm not here to teach you trigonometry. So all I'm going to require you to use is to be able to use a trigonometry function on your calculator. And you may not necessarily understand the function or be proficient in it, but the trigonometry functions, the one we're going to use here, the sine function, is available to you. The only thing you have to watch out for is sometimes things don't go well if your calculator is not set to degrees. It could be set to other kind of units like radians or grads or something else. So if you end up getting goofy results, it's possible that your calculator is not set to the right units for angles, which we're going to use. We're going to use degrees. So anyway, so this mathematical derivation is using a variety of substitution. I think on that page they do substitution about 3 times, and all they're using is several things that you already are familiar with. For instance, the length that a light ray travels would use the speed equation. So speed is distance divided by time, so distance would be speed times time. So you can see on this sketch where they're using speed times time, v times t. And also they've sketched in a couple of right triangles, which allows trigonometry to be used. And so just using the definition of of the sine function, which is the opposite side over the hypotenuse. These two triangles end up sharing a hypotenuse, so it ends up allowing some mathematical combinations. The other substitution that you can see going on in this page is using the index of refraction equation, C over V. And there's some substitution going on there. So anyway, so at the end of the page, we end up having an expression which allows you to relate the index of refraction of several different mediums to the angle of incidence and the angle of refraction. So let's write this down. It's the very bottom of the page. All right, so this part of the equation is related to medium 1, and this part of the equation is related to medium 2. So the way we're using this is medium 1 relates to where the medium through which the incident ray is traveling. Medium 2 is the medium through which the refracted ray is traveling. So index of refraction times the sine of the angle of incidence equals index of refraction times the sine of the angle of refraction. So let's do an example, top of page 683, to show you how this works. Okay, so this is example 35.2. So this is an example where light is passing from water into the air. In fact, let's do a quick sketch so we understand the scenario here. The example in the text doesn't give you a sketch, but let's go ahead and do that. So let's say you have a beaker of water and you have an incident ray. So the water is going to end up being your medium 1. And then it's passing out into air, which will be your medium 2. We have a normal line. And then remember, let me erase this here. So remember, as the light ray goes from a more dense to a less dense medium, the light ray will refract away from the normal line. So it'll look something like that. So the question in this example is, we have an angle of incidence of 35 degrees. What is the angle of refraction? And from your table earlier in the chapter, index of refraction is given for water as 1.33. So we're given angle of incidence equals 35 degrees. The index of refraction for water is 1.33. Now we also need the index of refraction for air to be able to use in this equation. So what is the index of refraction for air? It doesn't show up in our table. Well, remember we said that the speed of light in air is the same as the speed of light in a vacuum. So it's 1. You can always just use a value of 1 for index of refraction for air. All right, so now we have, let's go ahead and modify our equation here. So the incident ray is coming from the water, so I'll put the subscript W here, and then subscript air for the refracted light ray. So we are solving for the angle of refraction. So use algebra to solve for that. Sine of the angle of refraction is equal to so once you manipulate the equation, it looks like this. So the index of refraction for water is that, and times the sine of the angle of incidence, which is that, divided by the index of refraction for air, which is that. So if you plug that into your calculator, that ends up being 0.763. However, that's not the answer. We just solved for the sine value of the angle of refraction. So in order to get the angle of refraction, then you need to use the inverse sine. So on your calculator, all models of calculators should be like this. I have the sine button here, and the shift function just above it is sine to the -1. That would be your inverse. So you have to use the inverse sine function. So this ends up being, the angle is the inverse sine of 0.763. And if you calculate that correctly, you end up with 49.7 degrees. So when you come up with an answer, you always have to look to see whether it makes sense. The angle of incidence was 35, and then we said the light ray refracted away from the normal line. So the angle of refraction has to be higher than the angle of incidence, and our answer tells us that that indeed was true. And then we're going to do one more example. The next example on page 683, example 35.3, is actually what you're going to be doing in, one of the things you're going to be doing in your lab is once you're given the two angles, the angle of incidence, angle of refraction, then you can solve for an unknown index of refraction. And that will allow you to guess what the material is, what the medium is. So a sketch is provided for you on this one. What they're suggesting is you have some container that looks like this. You have glass and you have water, and the light ray is passing from the water into the glass. And as the light ray goes from the water into the more dense material, glass is more dense than water, the light ray turns towards the normal line. You're given angle of incidence is 40 degrees, angle of refraction is 33.7 degrees. We can look up the index of refraction from water from the table, and in water is the 1.33. And even though we know that this material is glass, there are lots and lots of different recipes for glass. All glass is not created equal. So different varieties of glass, different recipes for glass may have different indexes of refraction. So you're just asked to solve for that here. So this is we'll put a subscript G for the glass. So index of refraction for glass . Once you manipulate the equation to solve for index of refraction for glass, plug in your known values. 1.33 for water, sine of the angle of incidence, which is 40 degrees, divided by the sine of angle of refraction, which was given to you as (33.7 degrees). You're not going to use the inverse sine function here. You're just solving for index of refraction directly. So if you plug that into your calculator, that ends up being 1.54. All right, let me give you a couple of problems to work on. End of chapter problems. Okay, so end of chapter problems 35.5, 35.8, and 35.10 to practice what we just talked about in terms of Snell's law. All right, that's it for today.